Hello everyone. Today we are going to have an interesting topic called diagonalization of a matrix of order 2 by 2 with arithmetic and geometric multiplicity. So before moving on to this diagonalization process, let me know some basic definitions that we need to know. So the first one is diagonalizable. A square matrix A is said to be diagonalizable if we can able to find an invertible matrix P such a way that it should satisfy D equal to P into A into P inverse, where A is the given original matrix, P is the matrix where the columns are the eigenvectors of the matrix A. P inverse is the inverse of the matrix P, and D is the diagonal matrix whose diagonal entries are the eigenvalues of A. Next, the arithmetic multiplicity it is how many times the eigenvalue has been appearing in the characteristic equation. And the geometric multiplicity is the number of independent eigenvectors that has been arrived for the given eigenvalue. So this is called geometric multiplicity. In another way, we can able to find this geometric multiplicity with the help of the dimension of kernel of A minus lambda I. So here lambda is nothing but the eigenvalue, and or else we can able to find the same geometric multiplicity with another formula called the geometric multiplicity of the given eigenvalue is nothing but the dimension n minus the rank of A minus lambda I. And the relationship between the arithmetic and geometric multiplicity is the geometric multiplicity of the eigenvalue is always greater than or equal to 1, and this geometric multiplicity should be less than or equal to 1. And in this case, if for any eigenvalue the geometric multiplicity and the arithmetic multiplicity is equal, then if this holds for each and every eigenvalue of the given matrix, then we can say the matrix is diagonalizable. Now let us move on to the procedure that we have to follow to find the diagonalization of a matrix. The first step is we have to find the eigenvalues of the given matrix with the form of A minus lambda I. And next the eigenvectors has to be found with the help of any two methods. Here I have displayed two methods, cross multiply method or null space method. And after finding these two eigenvalues and vectors, we have to check the arithmetic multiplicity and geometric multiplicity is equal for each and every eigenvalue. Once this three steps have been done, then we can find the diagonalization matrix of form P, where P is nothing but it is the column vectors, that is the eigenvectors of the given eigenvalue. And after finding this matrix P, we have to compute the inverse of the matrix P, and we have to verify this expression called P A P inverse, and it should be equal to D. Now let us explain this methodology with the help of a simple 2 by 2 matrix. Let us take a matrix A of order 2 by 2 where the entries are 4, 2, 1 and 3. So as the first step we have to find the eigenvalue. So the eigenvalue have been derived with the help of determinant of A minus lambda I. It should be equal to 0. So let us take A minus lambda I. So from this matrix A, it can be written as 4 minus lambda, 2, 1, 3 minus lambda. Now for this matrix we have to find the determinant. So after finding this determinant, the expression has been reduced in the form of quadratic equation which involves lambda, and after factorizing this expression the eigenvalues are derived. So here I got the eigenvalues are 5 and 2. Now let us find the eigenvector for each eigenvalue with two methods. The first method I am going to use is null space method. So now let us find out the eigenvector for the eigenvalue 5. So now let us take lambda equal to 5 and consider this expression A minus, in the place of lambda I have substituted 5. So A minus 5i into x is equal to 0. So if I consider this A minus 5i, the given matrix has been reduced as minus 1, 2, 1 and minus 2. So here we can able to find this is the matrix of order 2 by 2. After the row elementary operation, I can check the rank of this matrix is 1, which means if the rank is 1, there is one free variable. So if I consider the vector x and y here, and if I make it as a linear equation, and if I equate it to 0, then I'll be getting one equation. So minus 1 into x plus 2 into y should be equal to 0. So from this I can able to find x equal to y. Since I have dependency of these two variables, I'm just considering y equal to t. So if y equal to t, then x is equal to 2t. So if I take t outside, the eigenvector I'm getting is 2 and 1. And similarly, the same methodology has been followed to find the eigenvector for the eigenvalue lambda equal to 2. Now let us consider this expression a minus 2I into x equal to 0. So here the given matrix has been reduced as 2, 2, 1 and 1. And since here each row is a scalar multiple of another one. So here the rank of the matrix is 1, which means I can able to find one free variable. So suppose if I multiply x and y here, and if I consider linear equation and equate it to 0, I am getting the equation of 2x plus 2y equal to 0. From this I am getting x plus y equal to 0. So if I consider y equal to t, then my x is equal to minus t. So taking y outside, I can get my eigenvector for the given eigenvalue 2 is minus 1 and 1. So here I am going to consider another methodology where I am going to find the eigenvectors using this cross multiplication method. Previously I have used null space method. So the same eigenvectors can be found by using this another methodology called cross multiplication method. So here I have a formula that suppose if I have a matrix of order 2 by 2 where the entries of the matrix are denoted as A, B, C and D, then the eigenvectors can be derived using the formula as minus B A or D and minus E, where these two eigenvectors are proportional and either of the eigenvector is valid. So in this case, I am just considering my eigenvalue lambda equal to 5 and considering the matrix A minus 5I. So this matrix has been reduced to minus 1, 2, 1 and minus 2. So based on the previous formula, if I take my A is minus 1 and B is 2. So based upon the formula, minus B means 2 times minus into 2, and for A it is minus 1. So I am getting minus 2 and minus 1. And for this methodology, you should follow that the eigenvector what you found, if there is any scalar multiples, you should remove it. So here I have minus 1 as a scalar multiple, which is common for both the numbers minus 2 and minus 1. So after removing that, the eigenvector I am getting is 2 and 1. Similarly, I am considering eigenvector for the eigenvalue lambda equal to 2. So A minus 2I. So for this, the reduced matrix is 4 minus 2, 2, 1 and 3 minus 2. So this reduced matrix is 2, 2, 1 and 1. So according to the formula, my A is 2 and B is also 2. So if I take my minus B is minus of 2 and 2. So here I have the scalar multiple 2. So if I take 2 outside, then the reduced vector is minus 1 and 1. So this is the eigenvector for the eigenvalue 2. So the conclusion is, here in this matrix I have two eigenvalues and I have found one eigenvector for each eigenvalue. Next, the main process is we have to check the arithmetic multiplicity and the geometric multiplicity for each and every eigenvalue. Now let us take the eigenvalue lambda 1 equal to 5 and lambda 2 equal to 2. Here in the characteristic equation, these two roots have come of degree 1, which means the arithmetic multiplicity is nothing but the number of times this root comes. So here the root 5 comes for one time and 2 comes for one time. So the arithmetic multiplicity of 5 and 2 is 1. Now let us check the geometric multiplicity. So here I am going to consider the formula, the dimension of the kernel of A minus lambda I. So let us take A minus 5I. I am considering the geometric multiplicity for the eigenvalue lambda equal to 5. So here in this matrix, here I told you that these two rows are independent. So the rank of the matrix is 1, and after doing this row elementary operation, here the kernel is nothing but the number of rows which have completely 0. So that is nothing but the kernel. So the dimension of kernel of this matrix A minus 5i is nothing but 1. Or else I can find this geometric multiplicity in another form. Like this is another formula. So the geometric multiplicity of the eigenvalue 5 can be denoted by 2 minus rank of A minus 5i. This 2 is nothing but, this is the dimension of this matrix. The dimension of the original matrix is 2, and the rank of A minus 5i. The rank is nothing but the number of linearly independent rows, or I can say the number of rows where the rows are not completely 0. So here in this case, there is only one row which is not completely 0. So here the rank of the matrix is 1. So 2 minus 1 is 1. So this is another way of finding the geometric multiplicity. So here I have explained the two methodology to find the geometric multiplicity of the eigenvalue 5. Now let us find the geometric multiplicity for the eigenvalue 2. So let us take the same expression A minus 2i. So here I have two rows of linear independent form. So after doing that row elementary operation, I can make the second row is completely 0, which means this is the kernel of the matrix A minus 2i. So the dimension of kernel of A minus 2i is 1, and this same dimension or this geometric multiplicity of the eigenvalue 2 can be derived in another form by using this formula 2 minus rank of A minus 2i. I told you before, this 2 is nothing but the rank of the, the dimension of the original matrix, and this rank is nothing but the number of rows which all the entries are not equal to 0, which means there should be at least one entry should be not equal to 0. So in that case, this matrix have one row which is not completely 0, which means there exists at least one entry which is not equal to 0. So in that case, the rank of this matrix is 1. So 2 minus 1 is 1. So now let us move on to the conclusion of the problem. So here we found two eigenvalues 5 and 2, and the arithmetic multiplicity of the eigenvalue 5 is 1 and geometric multiplicity is 1. And similarly for the eigenvalue 2, the arithmetic and geometric multiplicity is 1. So for in this case, these two eigenvalues have arithmetic and geometric multiplicities are equal. So in this case, I can able to say that this matrix is diagonalizable. So once we conclude about the diagonalization, now we can able to find the matrix P. This P is nothing but it is the collection of column vectors of the eigenvalues. So let us take those eigenvectors V1 and V2, make it as a matrix. Now I am going to find the inverse of the matrix. We all know the inverse of the matrix is 1 by determinant of A into adjoint of the given matrix. So after finding this P inverse, now let us recall this expression where if I multiply the matrix P and the diagonal matrix and P inverse, I should get the given original matrix. If it occurs, then I can say the matrix given is diagonalizable. So if you can able to multiply these three matrices, then you will be getting the original matrix A. So in this example, we have learnt that the matrix is diagonalizable. Now let us have another example where the eigenvalues have the arithmetic multiplicity more than 1. Now let us consider another example 3, 1, 0 and 3. Now let us check the diagonalizable for this matrix. So as the previous procedure, we have to find the characteristic polynomial for the matrix A minus lambda I, and here we can able to see that the root 3 occurs for 2 times. So which means the arithmetic multiplicity has come for 2 times. So now let us find the geometric multiplicity. So for the geometric multiplicity, the procedure is we have to consider A minus 3i and multiplying the vector x, it should be equal to 0. So if I do A minus 3i, I am getting the matrix of 0, 1, 0, 0, which means based upon the null space method, I can able to find the rank is 1. So here I have one free variable. So according to that, if I multiply x and y and if I equal to 0, I can get y equal to 0. So which means the variable free here is x. So from this I can find the eigenvector V as 1 and 0. Now let us check the given matrix is diagonalizable or not. We found the arithmetic multiplicity of the root is 2, but unfortunately the geometric multiplicity is 1. I can able to explain you that. Here we have found only one vector, which means the geometric multiplicity is 1. Or else we can able to find from here the number of completely 0 rows is nothing but 1. Or else I can say the dimension of kernel of a minus 3i is 1. So which means I can conclude that the geometric multiplicity of the eigenvalue 3 is 1. So here this expression is not equal. So I can conclude that the matrix which I have considered here is not diagonalizable. Now let us have another matrix where the eigenvalues comes more than one time. Now let us have this matrix. Here we have the eigenvalue which is repeated form. Now let us check the diagonalizable for this case. So following the same methodology, the characteristic polynomial is 3 minus lambda the whole square, which means 3 the root comes for 2 times. So the arithmetic multiplicity is 2. Now let us find the geometric multiplicity. If I consider a minus 3i, this becomes completely 0 matrix. So the dimension of kernel of a minus 3i is nothing but the number of rows which are completely 0. So in that formula, here the dimension of kernel of a minus 3i is 2. So it is nothing but the geometric multiplicity. So in this case, for the eigenvalue 3, the arithmetic multiplicity and geometric multiplicity are same. So for this matrix, I can say the given matrix is diagonalizable. Now let us find the eigenvectors. So a minus 3i into x is equal to 0. For in this case, I am getting 2 rows are completely 0. So for that case, all the vectors are satisfying this equation. So we can take the 2 independent vectors. So let us take v1 as 1, 0, v2 as 0, 1, 1. So let us consider these 2 vectors, eigenvectors, or the eigenvectors for the given eigenvalue 3. So from this we can conclude that the given matrix A is diagonalizable. Since it is diagonalizable, let us construct the matrix P. So this matrix P is constructed based upon the eigenvectors 1, 0 and 0, 1, 1. And we know the diagonal matrix is nothing but it is the diagonal matrix where the diagonal elements should be the eigenvalues of the given matrix. So in that case, for this problem, the diagonal matrix is 3, 0, 0 and 3. So if I consider this expression, so for this problem, the P matrix is nothing but identity matrix. So the inverse of the matrix P should be also identity matrix. So it obviously satisfies my given expression. So this is another matrix where explains us that a matrix is diagonalizable.